Okay, so let's do some problems from section 3.4, concavity and the second derivative test. We'll do exercises number 5 and 13. It says, in those, determine the open intervals on which the graph is concave upward or concave downward. We're going to base our work off of theorem 3.7, test for concavity, which says, let f be a function whose second derivative exists on an open interval I. So we're going to assume, well, actually we can look at this function and we know that it's continuous and differentiable on all of the real line. So we have the requirements of theorem 3.7 satisfied. So it has two conditions there. If f double prime of x, the second derivative, is greater than 0 for all x in I, then the graph of f is concave upward on that interval. If the second derivative of our function is less than 0 for all x in that interval, then the graph of the function is concave downward, right? And then concave upward means that we have this function whose the derivative is ever increasing, right? So our rate of change is always getting more and more and more. So if we look at that, that means that if we plot a tangent line, right, our function will always be above our tangent line. That's one way to look at it. Another way to think about it is that as you move to the right, the slope of your derivative is always becoming more, right? So then this is a negative slope, this is a zero slope, this is a positive slope, and if we were to move more to the right, this would also be a positive slope, but it would be more than what it was here. So that's what concave up and concave down means. Concave down means the inverse. As you move to the right, our derivative is always getting less and less and less, or more negative. So more negative if it is already negative. So in number 5 we have this x squared minus x minus 2. It's easy enough to find just by basic power and some rules what the derivative is. The first derivative is 2x minus 1, the second derivative is 2. So we see, based on this, that for any interval that we choose, and since our function is defined on the entire real interval, on the entire real line, our second derivative equal to 2 means that our second derivative is always greater than 0 for all x in an interval from negative infinity to infinity, or all of the real line. So we can say that this function is concave up for the entire real line. Okay, so that was a really easy one. And, you can kind of see that based on the fact that this parabola is pretty much this function. Maybe the origin is offset a little bit. We don't have the origin specified where it would be in this graph, but this is what the graph of that function would look like. And as you move to the right, the derivative is always increasing. So how about number 13? I don't know what the function looks like in number 13. I know that there's going to be a vertical asymptote in number 13. We have our definition here, x squared plus 1 over x squared minus 1. X squared minus 1 can be factored into x plus 1 times x minus 1, so we know that there's going to be two vertical asymptotes, right? We know that x plus 1 is never, or x squared plus 1 is never 0, right? Because even if I put in 0 here, I get 0 plus 1, so I'm greater than 0. If I put in a negative number in here, I'm going to get out a positive number, and then I'm going to add 1. If I put in a positive number, and I get a positive number, and then I'm going to add 1. So this function will never actually be equal to 0. So the sign of this function is always going to remain the same, no matter what. So if I had, let's say, and we can even plot this, right? So it's probably going to remain. So if I had a number which was slightly less than 1, let's say, or negative 1, let's say negative 3, right? If I had negative 3, the sign of this function is all determined by what occurs in the denominator. The numerator is always positive. So let's use a test point, something less than negative 1. We'll try out maybe negative 2. instead of negative 3. So it's going to become negative 2 minus 1, so that's going to be negative, and negative 2 plus 1, that is going to still be negative. So we're probably going to get something to the right of negative 1 that looks something like that. If we look at the graph of this, we see something akin to what we were talking about, right? So we have a vertical asymptote at negative 1, a vertical asymptote at positive 1. Our function is all positive to the left of that. If we had put in a test point of, let's say, 0, we would have come up with a negative number here, right? 0 plus 1, 0 minus 1, so we have 1 over negative 1. It's negative. So our function is all negative between negative 1 and positive 1, and all positive if we had put in a test point here, like, let's say, positive 2. We would have gotten out probably whenever this is a positive number, and we would have seen that it would be all positive from 1 for all numbers greater than 1. So now we kind of know what this function looks like, and we want to determine whether or not it is concave up or concave down. We can take a look at the graph of the function and come up with a guess. If we set out a bunch of test points, and I've laid out, kind of 3, and I'm not talking about test points like we evaluate this numerically, I'm just talking about we kind of look at this, right? And just looking at it graphically, if I were to lay out these little points and I were to say, well, what does the tangent line look like through those points? Well, the tangent line through this one might look something like that, maybe a little bit shallow here, but maybe still positive. And here, as I move to the right, I see that the rate of change is increasing, right? And then as I move a little bit more to the right, it is increasing even more, right? So my guess might be, based on what I look at, that for less than negative 1, I might have something that is concave up, right? Because as I move to the right, the rate of change is increasing. Now, how about between negative 1 and positive 1? Well, here I have a rate of change here, which is very positive, right? Here I have a rate of change which is 0, and here I have a rate of change which is very negative. So as I move from the right to the left, from the left to the right, I see that I have a rate of change which is started out as very positive and got to be very negative. So I might say that between here and here, I have something which is concave down. And here I have a rate of change which is very negative, right? Here it is still negative, but not as much as what the rate of change was at this previous point. And then here I have another rate of change which is still negative, but it is less still, right? So as you move from negative 1, numbers which are slightly more than negative 1, over to infinity, maybe I still have a negative rate of change, but less negative than when I started, right? So it's still, my rate of change is increasing as I move to the right here. So here, I would say maybe that this is concave up. And that's a guess. I need to actually do and go through the work. So let's go through the work. My function is x squared plus 1 over x squared minus 1, right? So let's use let's find our first and second derivatives. So we can use the quotient rule, right? Down squared times over, or below, down d up minus up d down. So we have down, derivative of up is 2x, minus up, x squared plus 1 times 2x. And then we do some simplifications, right? We can, let me go into another layer here. We have 2x, and we distribute 2x into x squared minus 1, comes 2x cubed minus 2x, and then we distribute 2x into this, so we also have to distribute this negative sign to both terms here. You could do either one either way. Doesn't matter which one goes first as long as you do multiply everything through there. So we have 2x cubed minus 2x cubed, that cancels. We have negative 2x minus 2x, that becomes 4x. So then we end up with this. So this is our first derivative, negative 4x over x squared minus 1 quantity squared. Do yourself a favor right now. Press pause, and see if you can get the second derivative. And I'll assume that you pressed pause and gave it a try. But if you didn't, let's go through it, or if you got stuck at all. Right here, we just use the quotient rule again, right? I'm not going to distribute this square term. I'm just going to leave it as it is and maybe use the chain rule a little bit when I get to the point that I have to take this derivative. So, again, quotient rule, I square the denominator, and it's going to be over down. So here's down, d up, right? Minus up, so minus a negative 4, so I just made that positive there. D down, so the derivative of x squared minus 1 quantity squared, we use the chain rule, we bring down the 2, and then multiply by what we had inside of here, and then chain rule says that we have to multiply by the derivative of what occurs on the inside here, so that's 2x. Distribute that 2x through, and you get the following manipulations, right? Combining, so on and so forth. So, you know what? Press pause again, and if see if you can get anywhere here. See if you can get this second derivative down here. So it's similar to what we had before, right, where we had to distribute through and then do some simplification. One point that you might get to is right here, and that's where we have some quantity that's up here. Now, one thing that I like to do is I say, all right, well, here I have polynomials on the bottom which are less in degree than polynomials that I have on the top. And what I'll try to do is see, hey, is the denominator one of the factors of this numerator? Because if it is, then something will cancel. And a lot of times these problems are constructed in that way. And I noticed that it is when I just give it a try with the old FOIL method and over regular integers, right? X squared minus 1 is indeed a factor of this numerator. So that'll cancel one of the factors that I have in this denominator. So I have here what remains of my derivative. Now at this point I'll take this x squared minus 1 and factor it into x squared plus 1 and x squared minus 1 and distribute my exponent of 3 to each of those terms. So this is the final answer for my derivative, right? So this derivative, if we want to determine whether or not it is greater than 0 or less than 0, is something that we will have to unfortunately save for the next video because we're out of time. So I will do the second part of number 13, which is determining the actual concavity in the next video.